Question 18 says calculate the cost of heating water to wash dishes if the sink is 48 centimeters long, 25 centimeters wide, and the water is 25 centimeters high. The tap water is 14 degrees Celsius and the final temperature before washing is 62 degrees Celsius. Power is sold to the consumer at 14 cents per kilowatt hour. Okay, so there's quite a few things that we need to do here. I'm going to discuss this kilowatt hour, what that actually means. But firstly, we'll need to work out the volume of the water and put that into a mass. So we've got 48 times 25 times 25. That will give me a value for the volume. 48 times 25 times 25. I get 30,000. Now that is centimeters cubed, or the same as a milliliter, and 1 milliliter of H2O, the water, has got a mass of 1 gram. So we've actually got about 30,000 grams or 30 kilograms of water. Okay, so it's about 30 kilograms of water. So in finding out, we're going to need to use our heat formula. Q is equal to mc change in T to work out the amount of energy. So that's going to be 30 times, we can use 4,200 for the specific heat capacity of water, and the temperature rise goes from 14 to 62. So we're looking at a 48, have I got that right? 48 degrees Celsius rise. So I can work out the number of joules that would be required. So that's going to be 30 times 4200 times 48, and I get 6048000 joules of energy. Okay, so that's how much energy I'm going to require. Now it says power is sold to the consumer at 14 cents per kilowatt hour. Now energy or electricity is sold or measured in kilowatt hour, and basically what that means, it means that you have a 1000 watt or a kilowatt appliance going for 1 hour. Now just imagine that. So it's 1000 joules every second, and it goes for 1 hour. So it goes for 60 minutes times 60 seconds. So that's going to be 3,600. So we're going to get this value over here, 3,600 times the 1000 is obviously going to be 3.63600. Sorry, I'm going off the screen here. Let me just redo that. It's going to be 1000 times 60 times 60, and that is 36, and then there are 5 zeros. So it's actually equal to 3.6 times 10 to the 6 joules. So that's how many joules there are in a kilowatt hour. Basically, you've got a 1000 watt appliance, 1000 watts, so it's 1000 joules per second. It's being used every second, and it's been used for 1 hour. That's the amount of energy that we're dealing with. So that is 1 kilowatt hour. That's what it means, is that many joules. So we need to therefore divide that by that, and we will see the number of kilowatt hours. So we've got 64,8000 divided by my answer, and I get a total there of 1.68 kilowatt hours, and obviously it's at 14 cents. I must multiply that by 14 cents. It's going to cost 23.52 cents to heat that water. Okay. Going on to question 19. The element of an electric jug has a resistance of 60 ohms and draws a current of 3 amps. Determine how much the temperature of 5 kilograms of water will rise if it is on for 6 minutes. Okay, so from the 60 ohms and 3 amps, we can work out the energy that is being provided per second. Let me just move to my formula booklet here. So we can use this formula over here, that the power is equal to I squared R. That will give me the power. So if I just bring that in, my power is equal to I squared R. So that is going to be, I is 3, so it's going to be 3 squared, don't forget the squared, times 60. So it's going to be 9 times 60, it's 540 watts or joules every second. And the total energy, the Q, because you are doing it for 6 minutes, 6 minutes here, because it's been done for 6 minutes, we're going to multiply that by 6 times 60, because obviously there are 60 seconds. This is 500 joules every second. So if we calculate that out, so we get 540 times by 6 times by 60, you get 194400 joules. Now this is used to heat 5 kilograms of water. So we use our formula Q is equal to MC, change in temperature. We've got this as 194400. The mass of the water is 5. We can take the specific heat capacity as 4,200, and that's the change in temperature. So obviously I'm going to need to divide that by 5 times 4,200, and I'll get my change in temperature. So divide by bracket 5 times 4,200, close bracket, and I get my change in temperature is 9.3 degrees Celsius or Kelvin, either way. Alright, doesn't seem very much, does it? But it is quite a lot of water. 5 kilograms of water, 5 liters of water. Alright, going on to question 20. Calculate the cost to heat 200 kilograms of water from 12 degrees Celsius to boiling point if it costs 14 cents per kilowatt hour. Okay, so remember 1 kilowatt hour is, if you take 1,000 watt appliance, I'll just go through this again, it's 1,000 watt appliance, and you let it run for 1 hour. The amount of energy, so it's 1,000 joules per second times 3,600 seconds, and it basically gives you 3.6 times 10 to the 6 joules of energy. That corresponds to 1 kilowatt hour. So we have got here, calculate the cost of, it's 200 kilograms that we're looking at here. Looking at 200 kilograms, and we're going from 12 degrees to its boiling point, so it's to 100, so we're going to need to raise it by 88 degrees. So let's work out the Q for that then. My Q is equal to MC change in T, so that's going to equal 200 kilograms times 4,200 times 88 degrees. That will be the total energy required to do that. So it's going to be 200 times by 4200 times by 88, and I get this number over here, 7392, and then there are 4 zeros. That's the total amount of joules. Now the number of kilowatt hours is obviously going to equal 73921234 zeros divided by 3.6 times 10 to the 6 joules. That will give the number of kilowatt hours that we have got, because this is the number of joules altogether, and this is the number of joules in a kilowatt hour. So I divide that by 3.6 exponent 6, and I get about 20.53 kilowatt hours. And it tells me here that it is 14 cents. I've got to obviously multiply the cost, will equal that times 14, and I get 287 cents that it would require. Okay. Oops, doesn't seem to be going. I have to leave that there. I'll bring it up like that. Okay, now we've got the next one over here. Determine the work done in moving a charge of 10 nanocoulombs, that's small n as a nanocoulomb, through a potential difference of 1.5 times 10 to the 2 volts. So with this, we've got our formula that V is equal to W over Q. So W is equal to V times Q. This isn't a very important formula. This is your definition for your volt. It's the energy per charge. So we have got here 1.5 times 10 to the 2 volts, and it's times 10 nanocoulombs. Now it's really important that you remember what these are. That's times 10 to the negative 9. And so the energy for that, when we do that, is going to be 15 times 10 to the negative 7 joules, or you could say 150 microjoules, something like that, or however you want to write that. Okay, and finally 22, we have here an electron in an electron gun of a picture tube is accelerated by a potential of 2.5 times 10 to the 3 volts. Calculate the kinetic energy gained by the electron in electron volts. So for this one here, we are going to use this formula here. So it's pretty straightforward. It's going to be 2.5 times 10 to the 3 volts times the charge of an electron in E. So it's actually going to be 2.5 times 10 to the 3 eV, or 2.5 kilo eV. This would be the way that we would write it. You could, if you wanted to, work out the actual velocity from that by knowing you could get your mass of an electron, put it equal to a half mv squared, and you could work out the velocity. But this is the kinetic energy that electron will have.